Welcome to the lesson on the brief history of onboard diagnostics, OBD development. In this lesson, we will explore the historical development of the onboard diagnostics, OBD system through the years. By the end of this lesson, you will be able to explain how OBD systems evolved from simple diagnostic tools to sophisticated systems in modern vehicles. Next, you will be able to discuss the role of emissions regulations in the development of OBD2. Finally, you will be able to explain the differences between OBD1 and OBD2. In this timeline of onboard diagnostics, we begin with the introduction of the Clean Air Act of 1970. Many changes were introduced along this journey, including the introduction of the Assembly Line Diagnostic Link, ALDL, in 1980, OBD1 in 1986, Shape and Pin Standardization in 1988, and OBD2 in 1996, which we are all still following to date. We will also discuss the comparisons between OBD1 and 2. The history of OBD, onboard diagnostics, can be traced back to the early 1970s when the U.S. government introduced the Clean Air Act. During this time, the U.S. Congress passed the Clean Air Act with the aim of reducing air pollution. One of the key provisions of this act was the requirement that all vehicles sold meet specific emission standards. This mandate had a significant impact on the automotive industry and paved the way for cleaner and more environmentally friendly vehicles. In 1980, General Motors, GM, introduced the Assembly Line Diagnostic Link, ALDL system. This system allowed for onboard diagnostics and monitoring of vehicle systems. During a malfunction, the check engine light would blink, indicating the presence of a problem. The ALDL system was an early step in vehicle diagnostics, providing a visual indicator for potential issues. In 1986, California implemented a version of onboard diagnostics, OBD regulations known as OBD1. This regulation was specific to vehicles in California and aimed at improving emissions control. OBD1 systems were designed to monitor and diagnose emissions-related components, contributing to cleaner air in the state. The implementation of OBD1 was a significant step forward in vehicle diagnostics and emission control technology. The year 1986 marked the introduction of the first generation of onboard diagnostics, OBD, systems, commonly known as OBD1. During this era, OBD systems were still in their early stages, and their shape, code, and design varied significantly depending on the vehicle make and manufacturer. These early OBD1 systems were simple and used analog sensors to monitor vehicle emissions. The Data Link Connector DLC is a multi-pin port that interfaces with the scan tool. The DLC location varied by make and manufacturer. Despite being the first generation of OBD systems, OBD1 had several limitations. The lack of standardization was a major hurdle, as each vehicle manufacturer had their own unique system design, making it difficult for technicians to diagnose and repair vehicles from different brands. OBD1 systems also had limited diagnostic capability and data storage capacity. They were primarily focused on monitoring emissions-related components and lacked the comprehensive monitoring and advanced sensors found in later generations. Code interpretation was another challenge with OBD1. The diagnostic trouble codes, DTCs, generated by OBD1 systems were often manufacturer-specific and required specialized knowledge and tools to interpret correctly. This made the diagnosis and repair process more complex and time-consuming. Additionally, proprietary diagnostic tools were often necessary to access and retrieve data from OBD1 systems. These tools were specific to each manufacturer and added to the cost and complexity of diagnosing and maintaining vehicles. In 1988, a significant development took place in the world of OBD with the introduction of OBD2. One notable aspect of OBD2 was its shape and pin configuration standardization. This standardization was achieved by the Society of Automotive Engineers, SAE, ensuring consistency and compatibility across different vehicles. The OBD2 adapter cable consisted of two ports. One port connects to the scan tool, and the other connects to the vehicle's OBD2 port, as depicted in the image on the left. The image on the right is a standardized OBD2 DLC in a vehicle. By the 1990s, OBD2 had become the standard in the U.S. and was mandated by law. These systems provided standardized error codes and diagnostic information, making it easier for mechanics to identify and repair issues with vehicles. OBD2 mandated several key specifications. First, it specified the data link connector or DLC type and its pinout configuration. This standardized connector made it easier for technicians and diagnostic equipment to connect to the vehicle's OBD2 system. Another important aspect of the OBD2 government mandate was the location of the DLC. It was required to be easily accessible to technicians, typically found within a specific range from the driver's seat. This standardized placement ensured convenience and consistency across different vehicles. OBD2 also brought a standardized list of diagnostic trouble codes, or DTCs. This meant that the same set of codes would be used across all vehicles, regardless of the manufacturer. This standardization made it easier for technicians to interpret and troubleshoot issues based on the DTCs provided by the OBD2 system. Now, let us compare OBD1 and OBD2, two generations of onboard diagnostics, OBD systems, that have played a significant role in vehicle diagnostics and emission control. One of the key differences between OBD1 and OBD2 is the time frame of vehicle support. OBD1 was primarily designed to support vehicles manufactured before 1996, while OBD2 was introduced to support vehicles manufactured from 1996 onwards. Another notable distinction is the standardization of the diagnostic port. OBD1 systems did not have a standardized port configuration, which means the port and pin layout could vary between vehicle manufacturers. This lack of standardization made it more challenging for technicians and diagnostic equipment to connect to the OBD1 system. In contrast, U.S. law required a standardized OBD2 port for vehicles. This mandated standardization made it easier for technicians to access and communicate with the OBD2 system, as diagnostic tools could be universally compatible across different vehicle makes and models. Let us continue comparing OBD1 and OBD2. OBD1 systems relied on a flashing light to communicate DTCs. When a malfunction occurred, the OBD1 system would cause the check engine light to flash in a specific pattern, indicating a corresponding code. Technicians had to count and interpret the flashes based on the manufacturer's code tables. On the other hand, OBD2 introduced a dedicated list of standardized code numbers. When a fault occurs, the OBD2 system generates a specific diagnostic trouble code, which can be read using a diagnostic tool. This standardized list of codes makes it easier for technicians to identify and diagnose issues accurately. Another distinction lies in the location of the DLC, the interface used to connect to the OBD system. In OBD1, the DLC could be located anywhere on the vehicle, depending on the manufacturer's preference. This lack of standardization made it more challenging for technicians to locate and access the DLC. In contrast, OBD2 regulations required the DLC to be located within 3 feet of the steering column and easily accessible to the driver. This standardized placement ensured consistency and facilitated straightforward access for connecting diagnostic tools. Let us now summarize the lesson on the history of OBD development. The history of OBD can be traced back to the early 1970s when the U.S. government introduced the Clean Air Act. Early OBD systems were simple and used analog sensors to monitor vehicle emissions. The main differences between OBD1 and OBD2 are the level of standardization and the type of diagnostic information provided. Today, OBD systems are found in all modern vehicles and are a critical tool for diagnosing and repairing problems in a vehicle's engine, transmission, and emission system. Thank you.